Sure, we were looking at this fork function. So we were talking about processes. Fork is one way to create a process. Uh-oh. Well, looks like. All right, give me a second to restart PowerPoint because it looks like I've lost my user interface. Oh, nice. There we go. Yes, there we go. This one. And this one. All right. Let's try that again. Okay, so we're looking at this fork function. The fork lets a process create another process. And so the current process becomes the parent of the child process that it forks. So both processes run in their own separate memory spaces. And the contents of both memory spaces are identical immediately after fork is called. Right? So you call fork, and then you basically get 2 copies of your process running. The parent process resumes running on the line after the fork, and the child process starts running on the line after the fork. Right? So after the fork call, both processes are now running, maybe in parallel, but they're both running now. Right? So there's a little example program here where we have x and y. If you fork to create a child process, then both processes print out the values of x and y. Right? And then there was this next example here. So in this example here, there's a header file we haven't seen before. So it's the header file errno, or ERRNO. So errno is one of the mechanisms that C uses to indicate that an error has happened. It's not the clearest mechanism that's ever been invented. So notice here that you fork a child process here, or you try to fork a child process here. Right? Now, if this fails, then 2 things actually happen. So number 1, that ID gets set to -1. Right? But the other thing that happens is that this variable called errno gets set somewhere. So errno is a variable that's set by system calls and some library functions when an error happens. Right? So an error happens, there's no exceptions in C. So we can't. So there's no way to. So we don't throw. There's no way to throw an exception or something like that. Sometimes the function will return an error value, right? So that in those cases, the programmer is responsible for testing the return value. Sometimes the function also sets this value called errno, and again, the programmer is responsible for looking at the value of errno, right? So the value the value of errno is always available to the programmer, right? But it only matters, so it's only significant when the return value of the call indicates an error, right? So the function has to return a value that indicates that a problem has happened, right? If that happens, then you can look at errno. Well, you can always look at errno, but if that happens, you can look at errno to find out maybe more information about why the error happened, right? So it's a very primitive form of error handling in C. The other problem is it's not exactly clear which functions set errno. So there's no standard way of there's no standard in the library, in the C standard library, that says a function must set errno if failure happens. Right? And so if you click on that link there, you'll get a list of functions in the standard library that can set errno. So if you scroll through here, you'll see that there are some, right? And if you keep on going, so if you just read the documentation for it, you'll see that there are functions that set errno to indicate that an error has happened. Right? So that's one of the standard ways. That's one of the several non-standard ways that C uses to indicate that a problem has happened. Right? Okay, so fork is a bit odd in that it returns twice. Most functions that you use in C, they only return one value. Fork returns 0 in the child process, and it returns some non-zero value in the parent process. So the parent process gets the ID of the child process that's created. The child process, there is no process created, so it just gets the value 0. And the two different values allow you to figure out which process is the child process and which one is the parent process. Right? So that's why back here, right? If you look at the returned ID and it's 0, then you know this is the child process, right? Boop, boop, boom. Right? Otherwise, it's the parent process that's running. Right? So you can do something in the something different in the child process compared to what you do in the parent. Okay, so fork basically creates a identical copy of memory for the two processes. Right? So there are some consequences related to this. Right? So any data that might be sitting in an input or output buffer, that also gets copied. Right? So a process, when you run a process in C that runs on a desktop computer anyway, you get standard in, standard out, and standard error. Right? That process can write to standard in, standard out, can write to standard out or error, can read from standard in. Right? When doing so, there may be information that's in the buffer of those streams. Right? And so when you fork a process, the child process also gets those buffers. Right? So they get standard in, standard out, and standard error, and whatever information is stored in the buffers of those streams. So you can write a little program like this, where we print out, the parent process prints out hello world. Right? Now remember, standard out is line buffered on Linux. Right? So in other words, nothing appears, or if you print out a small string and there's no new line character, then the way printf works, or the way that C prints out the string, is it waits until more information shows up on the buffer. Right? So it waits until there's a new line, or if there's sufficient information to actually bother doing the output. Right? Again, because output's expensive compared to any other process. Right? So when you print this, this probably goes into the standard out buffer, right? But doesn't actually appear on standard out. Now when you fork, right, the child process gets a copy of the standard out buffer. And then when you return 0, so the process, both processes end, right? Because this is the main function. So both processes end, the buffers get flushed. So this program here almost certainly prints hello world twice. So this is 3, and it does, right? So it prints out once. Now I don't know, oh, that's probably from the parent process, right? And then that's from the child process, probably. You don't actually know for sure, right? So the parent process prints out hello world, right? The child process inherits the buffer, well, inherits. The child process gets a copy of the buffer where hello world got printed into. When the program ends, the buffers get flushed, and so you end up with hello world twice. Okay, so so basically what's happening here is that the child inherits. I mean, it doesn't really inherit. The child gets a copy of the parent's set of open file descriptors, and each file descriptor in the child refers to the same open file descriptor as the corresponding file descriptor in the parent. Right? So in other words, if there's an open file, if the parent process opens a file, right, and then forks a process, the child process can write to the same file, read or write to the exact same file that the parent is writing to, right? Because they both get the same file descriptor. All right, now why would, so fork, okay, so fork is normally what's used to create a child process, which then calls execv to run some other program. Right, so remember this execv function is the function that you can use to create, to call another program from within your program. Right, execv replaces the contents of the new program, sorry, execv replaces the contents of the running program with the new program. Right, and so that's fine, right? You can replace the contents of the child process with your new program, right? But your parent process still keeps on running. Right? And so when I showed you execv the first time, we just had one process. We replaced the contents of the process with some other program, right? So now you're going to have a parent process that creates a child. The child process calls execv and replaces the contents of the child process with the other program, right? This is exactly what your shell does when you run a command, right? So when you're in bash, right, and you type in, so remember bash is a process, right? So my shell here is actually a process running in Linux, right? When you type in a command like ls, right, the shell forks a new process to run the ls command, right? And then returns control back to me, right? Back to the shell, right? So ls doesn't take very long to run, so that's so you can't really see what's happening here, right? But when ls runs, it's actually running as a separate process, right? And so any command that you type into the shell gets forked. The shell forks a new process, uses execv to run the command in the copy of the shell. So here's an example where we're going to fork a new process from the parent. Right? In the child process, we're going to call the go to sleep program using execv. Right? In the parent process, right, the parent process is just going to print something out and then exit. Right? Okay, so when you run that program, right, the child process starts, right? So the child process goes to sleep, right? Nothing happens, right? And now when the child process finishes, right, it prints I'm awake. If you look at the right, so when you look at the output very carefully, right? So that's the parent process, right? So 452 is the parent, so that's the fork x4 program. Right? Its parent is 9, so that's my bash shell. Right? It creates a child process whose ID is 453. Right? Now the child process starts running, so you fork the child process. The process runs. Right? So there's your child process with ID 453. And the child thinks its parent is 452, which is good because that's what it is, right? So that's the process ID of the fork x4 program, right? Now the child runs, right? So there's the child running, right? It goes to sleep, so it calls the go to sleep program and then goes away for 10 or 15 seconds, right? Now notice what happens when it wakes up, right? So when it wakes up, that's the child process waking up, right? It thinks its parent is now process number 8, but it was, sorry. Right, it thinks it's 8, but the parent is process 452, right? But for some reason, the child now thinks it's 8, right? And so the question is why does the child process think it's 8? And it's because, right? So there's the child process running, right? It goes to sleep for 5 seconds, right? Now at the same time, the parent process is running, right? Now the parent process just prints out some information and then exits, right? So the parent process that created the go to sleep program, right, or the parent process that created the child program, the process that ran go to sleep, finishes before the child process finishes, right? So in other words, the parent process is done. So the child process now doesn't have a parent anymore because the parent process has completed, right? So when you look at that output and you read it really carefully, right, you'll see that the child process's parent changes. Right? Now the reason it changes is because the parent finishes before the child does. Right? And so we say that the child ends up being orphaned. Now Linux doesn't like orphaned processes, so in Linux, if a process gets orphaned, like the one we just had, right, then that process gets adopted by some other process. Right? And the details of this are beyond the scope of this course. Right? That's an issue that your operating systems course will look at. Actually, your operating systems course probably won't look at this issue. Right? This would be something you'd look at when you actually study an actual operating system in great detail. Right? Okay, so what happens if the child finishes before the parent? Right? So here's what happens when the parent finishes before the child. Right? The child gets adopted by some other process. Right? if the opposite happens, right, so the child finishes before the parent, now that's the way things normally happen, right? Parent process runs, so your main program runs, it makes a bunch of child processes, they all do their thing, right? If a child process terminates, then its parent is responsible for reading the exit code of the terminating process. Right? So remember when we're writing our bash scripts or we're writing C programs, right? The bash script exits with an exit status, right? A C program, the main function can return a value, which is the exit status of the program, right? Who's reading those exit statuses? It's the parent process of that process. It's the parent process that is responsible for reading the exit code, right? So the way it works in Linux is, until the exit code is read, the process ID of the child process is not released back to the operating system, right? And that's a problem because your child process, because the operating system only has a finite number of process IDs to hand out, right? So if the parent does not read the exit code, then the child process becomes what's called a zombie process. So here's an example. This is actually fork x5. Right? So it's the same program as before. Right? We're going to fork a child. The child is going to go to sleep for 5 seconds. Right? In the parent, though, the parent's going to sleep for 15 seconds. Right? So it's going to, the child process is going to finish before the parent process. Right? Nowhere in this else part of the if statement is there something that looks like the parent is reading the exit status of the child, right? So remember, it's the parent process that's supposed to read the exit status of the child process. And there's no function call here that looks like it's reading the exit status, right? So this is going to produce a zombie process. So if we run that program there, right? So it's running now. Okay, so the child process is done. I'm just going to interrupt this for a second and run it in the background. And then I'm going to do PS, right? Notice there's a process down here, right? So that's the child process, right, that ran go to sleep. Notice that it says defunct, right? So this is PS's way of telling you that's a zombie process, right? The parent process that started this thing never read its exit status, right? Now when the original process disappears, so when the parent process goes away, right, the operating system cleans up the zombie process. Right? Now, if the parent process doesn't go away, right? So if the parent process keeps on running, so if it's some very long-running program and it never reads the exit status of its child processes, right? You end up with a bunch of zombie processes lying around, right? And those zombie processes are occupying, or those zombie processes hold on to their process ID, which means your operating system can't reuse those process IDs for other processes. Right? So if you are ever in the situation where you're using fork or some similar mechanism to create child processes, it's your responsibility to read the exit status of those processes. Where is the, okay, here we go. Oh, this exam slide's wrong. I'll talk about the exam at the end of the lecture a bit. Okay, so the way that the parent process reads the exit status of a child is, the terminology is waiting on the child. Right? So you wait on the child to finish and then read their exit status. So waiting means waiting for the child process to terminate or stop, right? So when a process terminates, it has an exit status. It turns out when it stops, it also has an exit status, although it may not be the same status as when it finishes. Right? So when a process terminates or stops, it's possible to ask for the status of that process. Right? Now, the parent has to wait for the child, right? So there's a bunch of different strategies that you can use to wait for the child. Right? So strategy number one, the parent process does something and then it just waits for all the children to finish, right? Even though the parent process might not have anything else to do, right? So if you wait until a child process terminates or stops, right, the parent does nothing while waiting, so that's called blocking, right? So the parent process is blocked until the child process is finished. Right? Now, if you don't want to sit around doing nothing, so if the parent process has something else to do, right, then what it can do is every once in a while it can test to see if a child process has terminated or stopped. Right? And then it can do whatever else it needs to do. Right? Every once in a while it comes back and looks to see if any child process is finished. Right? So there you have to write code that basically polls all the children to see whether or not one of them has finished. Right? Option number 3 is that when a child process stops or terminates, then a signal is sent by the operating system to the parent process to indicate that a child process is finished. Right? So we can now handle that signal to deal with we can handle that signal to read the exit status of any child process. Right? The parent process can just keep on doing whatever it's doing. Right? When it sees the signal, it gets interrupted, and then it can deal with reading the exit status of the child. Right? So to wait for a child, you use the function called wait, which is probably not that surprising. Right? So the function wait will cause the parent process to wait for any child process to terminate. Right? So this one will wait for, so if your parent process creates 10 children, wait will just wait until any one of those children terminates. It returns the ID of the child that stopped. Right? On error, which shouldn't normally happen, you get back -1. Right? So here's a modification of one of the programs. Wait x1. Okay, so we're going to wait on a process now. Right? So here, the parent just prints out a bunch of stuff, right? And then it waits on the child. Right? So that's all it does. The the status code gets gets written to whatever status points at. Right? So I've got my exit status variable here. Right? Wait is going to write into the exit status variable the exit status of the child process. Right? And so the parent process stalls right here on the wait. Right? So it just sits here and waits for children to finish, right? And does nothing. So this is not the most it's not the most useful, it's not the most efficient use of resources if you do it this way. Right? But let's see what happens when we run this program. So this is wait. Is it actually wait? It's not actually wait. Sorry, it's one of the fork programs. Car, it's not that one. Is it this one? Parent. Wait, oh, it is. Okay, so it's number 5, sorry. 6. Okay, so we're going to this one and comment out this one. Okay. And so this is fork x6. Okay, so the parent process is going to run, right? It forks the child process. Oh, there it goes. The child process runs go to sleep, right? And now the parent process just sits here and waits for the child. When the child finishes, the parent can print out the exit status of the child, right? So that's nice. So that did not create a zombie process for us, right? Because the parent process waited until the child finished before exiting. So wait actually calls a different function. So wait calls the function waitPID, and waitPID returns the process ID of a terminated child. Right? Do I tell you what the inputs are? Yeah, here we go. Okay, so for this version of wait, you pass in the child that you want to wait on, right? So that's the ID of the child that you want to wait for, right? You have some options here. You can pass in wait any to wait for any child, and then you can pass in this other option here. Wait my group, which returns information about any child process in the same group as the calling process. So that the calling process is the parent process, right? Again, so exactly what's in a group is beyond the scope of this course, right? The status, that's where you store the the exit status of the child, and then there's a bunch of options that you can pass in as well. Right? So options is 0, wait until the child terminates or stops, right? Or you can pass in one of 3 options here. I don't think, let me just take a look at the program. I don't think I'm going to use one of those options. Is it, sorry, it's wait. Oh, come on. This one here. Yeah, so I'm just going to use 0 for that instead. Okay, so we're going to use waitpid in this case. It's going to produce the exact same output as before. Right, so you can also use waitpid, and that's going to wait, and that will do the same thing as before. It's just going to wait for the child process to finish, and then it's going to print out the exit status. Oh, wrong one again. Okay, so instead of just waiting around and doing nothing, you can write the parent process so that it simply regularly tests for the child process to terminate by calling waitpid in a loop. Right? This is where you use no hang as the option. Right? So w no hang, if you pass in that as your option, right, causes this function to return immediately instead of waiting if there's no child process ready to be noticed. Right? So if no child process is finished, waitpid returns immediately. If there is a child process that's waiting to be finished, then it also returns immediately, but then it also sets the exit status. Right? So again, it's the exact same program here. Well, it's almost the exact same program. So in the parent process, there's just an infinite loop now. Right? So loop forever. Right? Call waitpid to see if a child process is finished. Right? If you get back 0 from waitpid, then that means no child process has done any, no child process has completed yet. So here's where you can do something. Right? So I've just got a little function called do something that doesn't really do anything. Right? But now the parent process can do something. Right? When it finishes doing something, it comes, but the loop runs again. Right? So again, call waitpid. Right? If the result is 0, go off and do something. Right? Come back again, call waitpid. If the child process is finished, then you come down to here and you finish and you read the exit status of the child. Right? Here, when I read the exit status of the child, I actually break out of the loop. Right? I don't think do anything does anything interesting. Let's see what happens. Do something. Oh yeah, so this this doesn't do anything interesting. It just prints that the parent's doing something, right, and then goes to sleep for 1 second. Where is? Okay. Okay, so here, so the parent's doing something, it's doing something, it's doing something, it's doing something, and now it finishes. Right. So this is an example, this is not a very good example, but this is an example of what's called polling. Right? So here, when you look to see if a child process is finished, right, you're polling the child process to see if it's finished. Right? If it hasn't finished, then you go ahead and do something. Right? And then every once in a while come back, right, poll the child to see if it's done. If it's not done, do something, and so on and so on and so on. Okay, so either waiting for the child to finish or polling the child to see if it finishes, that relies on the parent process testing whether or not the child process has terminated or stopped, right? There's an alternative way to do this, and that's to rely on the operating system to send a signal that the child process has terminated or stopped. And this actually happens anyway, right? So whenever a child process stops, Linux sends the signal sigchild to the parent, right? And so the other way to do this is to have the parent listen for these signals, right? And so the way you listen for a signal is to use the signal function or sig action, either one of these two. Right? So to handle a signal, your program can define what are called signal handlers. Right? A signal handler is just a function that listens for a particular signal. Right? The signal function is easier to use than sig action. Right? But if you read the man page for signal, it basically says don't use it. Right? So the only portable use of signal is to set the signal's disposition to one of these two things. Right? The semantics when using signal to establish a signal handler varies across systems. So in other words, it's trying to tell you, look, depending on your operating system, the way this thing behaves is different, right? Do not use it for this purpose. I think I'm going to use it for that purpose anyway, though. So where is signal? Okay, so are we going to use signal? Yeah, we're going to use signal here. And just let me check signal 2. Still using signal. Okay, so we're using signal here because this is the easier way to do it. So the various signals that you can listen to on Linux, or at least my version of Linux, you can get by running the kill program and passing in -L as your option, right? Again, there's a lot of them. Most of them, but there's the ones that we're interested in are ones like sigchild, which indicates the child process is stopped. Sig alarm. So you can set a timer in C, and so the timer, when it finishes counting down, will send a signal to the process that started the timer. Right, so you can listen for timers. Sig int is what happens when somebody types Control C. Right, so if you want to interrupt the process using Control C, that sends sig int. Sig kill terminates a process. Sig term terminates a process, and sig t stop stops a process. So when you type Control Z, that's the signal that's sent. Right. To write a signal handler, you just define a function. Right now, signal handler underscore t, right, is just a type def. Right. So it's a pointer, right, to a function that returns void and takes int as its input parameter. Right. So it's a function. The parameter is the signal number that's passed to the function. Okay, so here's my, this is going to be my signal handler, right? So remember, it returns void, takes in an int, right? So my signal handler is called catcher, right? It takes in an int. The signals are just ints, right? Which means, so I think I told you in the last lecture that signals are very primitive, and they are, right? They tell you almost nothing, because all you get is an int value, right? So if the signal is equal to sig int, that's the Control C, right? So I'm going to listen for that signal. Now, instead of Control C stopping the program, right, the signal handler catches that signal and then does whatever it does here, right? So here I'm just going to print out that we detected that sig int was the sig int signal has occurred, right? If sig equals sig stop, I'm going to look for Control Z, right? So when this program sees the Control Z signal, it's going to print something else instead of stopping or terminating. Right? Now notice if you run this program, right, if you run a program with a signal catcher, you can't use Control C or Control Z to stop this program. Right? So there's going to be a warning in a second that tells you not here. Right? So in the main function of the program, right, I'm going to use the signal function to register that catcher function as a signal handler. Right? I'm going to tell the operating system to send sig int to that catcher function. If you uncomment both of these lines, right, then that catcher function will handle both sig int and sig t stop. Right? So it'll handle Control C and Control Z. There's an infinite loop here. Right? So because the program catches both of these signals, you can't stop this program in any meaningful way. So don't uncomment both of these lines in Windows, right? If you're running it, if you're running the Windows subsystem, there's no way for you to stop the program except to close your Linux instance. Okay, so that signal function simply tells the operating system to use that function to handle that signal. And so if you run that little program, I should check to see how it's been compiled last. Not that one, sorry, signal 1. So, okay, so this one can handle Control C, but it won't handle Control Z. Right, so it just sits here doing nothing, right? So it's got a little while loop here, right? So it's doing nothing. If I type control C, right? So control C is sigint, right? And this program is listening to sigint with this signal catcher here, right? And so it just prints out that sigint has been detected, and then it does nothing, right? Whereas control C would normally stop this program, right? Type it again, right? Still nothing happening, right? Control Z will stop that program, right? And then I can kill it manually myself, right? So notice that it's still running. Well, it's not running. It's still alive, right? It's stopped, but not alive, but not running. So now I can kill it, right? So I'm going to kill it with K9, and away it goes, right? So now it's gone, right? If you uncomment that line, so if you flip the comment around, then you can catch the other signal. Okay, so you can use a signal handler to respond to sigchild instead of blocking or looping, right? So in your signal handler, you're still going to call waitpid to look at the exit status of the child, right? There's a little program here that you can look at to see how this works, right? So we're going to, here we go. So there's my handler function that's going to listen for the sigchild signal. Inside the function, all you do is you loop, right? You call waitpid to see if there's a child that's done, right? If you get a value that's less than 0, that's very unusual, right? If you get a value that's 0, we're going to break out of the loop, right? So when you get 0, that means, if you get 0, that means there are no child processes waiting. Right? Or, sorry, no child processes have finished, right? If you don't get 0, right, then we're going to call this little function here that reads the that does something with the exit status. Right? And in the main function, we're going to fork a child. Right? In the child process is going to call go to sleep using execv. Right? The parent process is going to wait. Well, it's going to do something, right? And it's just going to, when the child process finishes, right, the signal will be sent to the parent process, which gets handled by the handler, right? And then the handler will print out the exit status of the child. Okay, so let's see what happens when we run that. Right, so there you go. So the parent's doing something, it's doing something, right? I'm not, there's no loop here, right? And okay, right? And so the child process finishes here, right? The signal handler catches the child process finishing, right? Prints out the exit status of the child process, so there's no orphan process or no zombie process here, right? And then the parent keeps on going and doing its thing, right? So this is just going to run forever. Oh, there we go. Okay, so I guess that's all that we want to cover this year in this course. The exam, I don't actually know the official date of the exam. Whatever Solus says your exam date is, that's the date and time. 23rd. So it's the 23rd. The exam is on OnQ, right? You're supposed to start when the exam, at the exam time, whenever it says you start. It's 3 hours long. There's lots of examples of old exams on OnQ already with worked solutions. I think there's 8 or 9 of them that are there. What else is there to say? It's on OnQ, it's not proctored. You are allowed to use whatever editor you're using to write your programs, and you should use an editor to write your programs. Right? If the question asks you for code, you should upload, you can just write the code in your editor and then upload the code. Right? So you don't have to copy and paste it into the window. Right? It's easier just to upload it. And that preserves all your formatting and stuff like that. Yeah?
Are we getting like a grace period after the exam output we go? Or?
I think there's, yeah, so normally I give you a 10 or 15 minute grace period. So 3 hours plus, yeah, so it's normally 3 hours plus 15 minutes. What else is there? Is there anything else? Anybody have any questions about the exam?
It's all C-based?
No. There's a little bit of bash. There's one bash question, one or two. Because wait, did we test you on? I don't remember. I think there's a part of bash scripting that you weren't tested on the midterm. So whatever is left over is could show up. But the rest is all C. Yeah. Any other questions about the exam?
Are you doing an exam review session on Friday or?
No, I'm done. That's it. Had enough, right? I got one more 8:30 class tomorrow, and that's it. Sorry?
Is it all coding questions, or is it like multiple choice, true or false?
That's a good question. I think it's primarily coding. It's going to be primarily coding questions. I think there's normally only one question where you have to write a complete program, right? So there's only one. There's only the last question. Are you asked to create a bunch of functions, make a main function, do blah 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 blah, right? The rest of them are all standalone questions, right? Write a function that does blah, write a line of C that does whatever, and stuff like that. Any other questions? All right, your assignments should start coming back later this week, now that I'm done lecturing. And I guess that's it. All right. You're welcome. Assignment question. Okay.